We're going to talk about how to jam nonlinear specifications into a linear regression. We call that nonlinear regression. We do that because academics are good at wringing every last drop out of any good idea. Good ideas are rare. We got to squeeze every bit of juice out of them. Linear regressions, OLS, are one of those good ideas we want to get some use out of. Nonlinear models are generically how the world works. Linear is a simplification or an admission that we just don't know that much. It's a first order guess. If you remember the Taylor series from calculus, any differentiable function can be approximated within a neighborhood by a linear function. Not every function in the world is going to be differentiable, but for a variety of cases, we're comfortable specifying the relationship should be smooth. The idea of higher order polynomials just spills right out of the Taylor series idea. How do we use a linear regression with a nonlinear term? Ordinarily, a multivariate regression sets y equal to beta naught plus beta 1x1 plus beta 2x2, etc. Well, what if for x2 we just move that 2 up? Call it x squared. For that matter, any nonlinear function of x, like log x. It works fine. It goes right on through. I showed this graph earlier. From BRFSS, here's income as people age. It's certainly not linear. Actually, these are estimated with what's called a generalized additive model, GAM. You can look into more details if you want. But first that graph goes up, it hits a peak, and then it slopes down. That's the over the hill of the old saying. So it makes sense to include age in a nonlinear specification here. I regress the y variable, income or cannabis use or whatever we're talking about, beta naught plus beta 1 age plus beta 2 age squared, plus some other stuff, plus the error term. Remember from calculus, how do I take the derivative of y? As age increases, well, that's going to be beta 1 plus beta 2 times age. That's the first derivative of that parabola. Often, as in the case we showed, beta 1 is going to be positive, beta 2 negative. So people's age increases with their wage at first. Then gradually the income increase on your birthday gets smaller and smaller. Eventually you roll over the hill. We find the peak by setting the derivative equal to 0, since that's the local maximum. For different signs of beta 1 or beta 2, it could be a min. And if you like that, you can now add higher order polynomials, x cubed, x to the fourth, go on and on. There are debates about how many to use, but you can test it. You can do a joint test whether all the coefficients on these higher order polynomial terms are jointly equal to 0. We talked about how to do that hypothesis test. Now note we would not do tests one by one and drop the squared term but leave the cube. It's kind of weird to think we'd have such precise knowledge about one of those polynomial terms but not any of the others. It's probably just an error of the test. Just as we put in squared or cubed or higher order polynomial terms, we can also put in logs. We're not in elementary school, so log always means the natural log. Base E, that's what makes sense. You could take the log of x, you could take the log of y, you could do both. Remember Jensen's inequality, the mean of the log is not the same as the log of the mean. One of the reasons use logs is for calculus again. Logs have an easy interpretation. In a regression, if I have log y on the left, each beta is interpreted as the derivative with respect to that x. Derivative of log is a percent change. So if I have log x instead of x on the right hand, then that coefficient is the change in y from a 1% change in x. And if I have log of x and log of y, then the coefficient estimates the, what percent change in y per percent change in x. So, those are slightly different formulations of the model, but you can make your choices about which one seems like a more sensible specification.